Okay, so this is basically the same thing that we just saw, the double integral. And again, what we need to talk about is when our region is not rectangular. So this is the case we just saw. This is our rectangular region. This is where the order doesn't really matter. It's really easy to switch the order. There's nothing big you have to do. So we're not going to do this one right now because this is very similar to what we just did. We could go from 0 to 3 in X first and then 0 to 2 in Y. Or we could go 0 to 2 in Y first and then 0 to 3 in X. We will get the exact same answer. Now, what we need to think about is when our region has boundaries that are defined in terms of functions. And this is going to take some getting used to. And this is one of the things we're going to practice a little bit today. So for example, maybe our top and bottom of our region are given in terms of functions of X. We don't have a lot of choices on order in this case because of the variability. These are going to be our outside limits, A and B. So we're going to integrate with respect to Y first, top and bottom, then with respect to X. All right. Has to. Our outside limits must be constants. If we need those to be constants because we need to have a final answer. Notice our inside limits can be functions of X because we're going to still integrate with respect to X in the next step. Same thing goes if we had side limits in terms of Y. Now we have to do in terms of X first and Y second. That's okay because Y is eventually going to get integrated out and we'll get left with constants. So the order of integration can very much matter sometimes. It's going to vary. I can't say it's always going to matter in this case and not always not in this case. It's going to vary from problem to problem. So some of them, if our boundaries are invertible, we can actually very easily switch the order of integration. And I'll show you what I'm talking about here. So let's take a look at an example. I'm going to do set up a couple different regions too. But we're going to start with this one. So now this one I'm not going to, we might work through, we'll see. Actually, we probably should work through one. I don't want to take too much time though either. So we've got this triangular region, all right? Once the region is not a rectangle, the limits are not all constants. If you do limits of all constants on this one, it'll be incorrect. And you cannot do limits of all constants and then just cut it in half because half of a rectangle is a triangle, because there's no guarantee that the function is constant over the rectangle versus the triangle. So here's how we have to approach these. So we take a look at our region, and our region is here, and we need to get, if we're not given a function for the boundary, we need to find it. Well, we've got a rise of -3 and a run of 5 and a y-intercept of 3. So this is nice and linear. So y equals -3/5 x plus 3. All right, let's talk about setting this up. Now, because I've already got this in terms of y, I pretty much got it set up to do y first. So let's do that. I'm going to show you both directions. What you want to look for on your region is a top and a bottom or a left and a right. Well, I've got a bottom of 0 and I've got a top of this function. So I can say, all right, well, I'm going to go from 0 to -3/5 x plus 3. And I'm evaluating this function 5 plus x plus 2y. And this tells me I'm going bottom to top. I'm going vertical, so I'm doing y first. So dy. Now we're going to go horizontal. So we're going to go from here to here. We've already got that point marked. This is the point 5, 0. So x is going to go from 0 to 5, and we're doing dx second. Okay. Now here's what's happening. Now what's happening is we're going from 0 up to the curve, right? So let me do this in a different color. So basically, both things are happening at the same time to fill in this triangle for us. So think of it this way. As y goes from 0 up to the line, x is going from 0 to 5. So as I'm drawing a line from 0 up to the line, well, now x is increasing from 0 to 5, and I'm getting a bunch of lines that just stack all over each other. Does that make sense, the way that's working? This is going up while this moves us this way. So it's kind of like one's constant. Yeah. And that's why these can be constant and these don't have to be. They don't both have to be in terms of functions. This takes care of the variability. This takes care of moving it across. Okay. Conceptually, that's what's going on. And I think that'll help as you start to set these up. Now, so you got to look for a definite top and bottom or a definite left and right. So we could have done in terms of x first, but that means if we're doing x first, that would switch the dx and the dy. That means we have to find the inverse of this function. So basically solve this thing for x. So what do we have? Y minus 3 times negative 5/3 equals x. And let's simplify that just a little bit. So negative 5/3 y plus 5. So now, if I want to, and this will be exactly equal, we have 5 plus x plus 2y. We're doing dx dy because I said we're switching the order. Now we're doing x first. It's going from 0 out to the curve. It's going from 0 to minus 5/3 y plus 5. And now y is going from 0 up to, and we have to use the y value, right? Let's go from 0 up to 3. These will give you the exact same thing. Right? So there are going to be ones where the order doesn't matter at all. And drawing the region is going to be very helpful. Now, the only thing that's going to happen different in doing one of these than the one I did earlier, when I plug in that upper limit, I have to plug in negative 3/5 x plus 3 and do the math on that. Again, that's okay because in the next step, we're going to be integrating with respect to x. All right. So I'm not going to do that right now because I want to save that for you guys to do, because there's nothing conceptually different going on. It's just algebraically a little more complex because it's not just a constant. Just take your time with it. Bless you. Thank you. Okay. Questions about setting either of these up? I want to focus, like I said, I want to focus more on the setup because the rest of this is just algebra. All right. Let's change things up just a little bit. I want to just show you one other thing. And we're not going to be able to cover all the examples. We're going to have all different sorts of regions, things of that nature. Let's do. We'll make kind of an interesting region so we can kind of play around with it. Let's say half a circle and a straight line, okay? So this is a half circle, it's above the XY plane. So that'd be y equals square root of 1 minus x squared. And just to make this simple, let's say this is y equals 1 minus x. Okay. Now, what I want to talk about, and I'm not worried about the function, I'm more worried, I'm just thinking in terms of setting things up. When we go to set up these integrals, depends on how many integrals we want to deal with, basically, because right now, if I go top and bottom first, which is what these are set up for, because these are both in terms of y, I have to break this into two separate integrals, because the top and bottom is different here than it is here. All right, so what that would look like is, let's just say we wanted the area of the, and we'll just do a general function. So what that would look like is we split it up here at 0. Let's see, that's going to be x equals minus 1. It's going to be x equals 1. And so if we were doing this some function over this region, and again, we are set up to do y first because these are already solved for y. We could do 0 to square root of 1 minus x squared. And then we could do, say it again. Yeah, -1 to 0. And that's doing dy dx. That only takes care of this part. We need to add on this part. Very similarly, 0 up to the curve, 0 up to 1 minus x. Again, we're doing f of xy, dy dx. And now 0 to 1. All right. Okay. Now, let's say we wanted to go the opposite direction. Okay. Let's say we wanted to do dx dy. What we would have to do is invert both of the functions. So we both basically, excuse me, both these would have to be solved for x. This one's easy, x equals 1 minus y. This one's a little trickier. You're going to square both sides. You're going to flip things around. So it's going to look real simple. X equals square root of 1 minus y squared. Now the problem is, notice where x is, right? This is on the negative side of the x plane. So this actually has to be minus to account for those negative x values. Now here's why this might be advantageous. Maybe not, depends on the function that we're integrating over. But now we can do this as a single integral. Because now I have a single left and a single right. So now integrating with respect to x first, so f of xy dx allows me to go from just left to right. So negative square root of 1 minus y squared out to 1 minus y. And now we're going to do our dy, which would be y equals 0 up to here, which is y equals 1. So these two would give us the same thing. The reason I did this though is I want to kind of see, because you're going to hear me say that, not just with double integrals, but triple integrals, is this idea of a definite top and bottom if you want it to be a single integral. Okay? That's what I mean when I say like a definite top and a bottom, or a definite left and right, because here, top and bottom is different than it is here. So that tells me if I decide to integrate with respect to y first, I need to do it as two separate double integrals. But because I only have a single left and a single right, I know if I do it the other direction, I only need a single double integral. All right, so that's why being able to draw the regions is going to be helpful, especially in the double integrals. Last thing I want to point out on this, remember that we said that the integrand is 1, what it's doing is calculating the area, right? All right, so I'm going to do that on this one because there's one last thing I want to show you, and I want to connect this to something you've done before. And so if I change the integrand to 1, well, then the very first thing I do when I take the antiderivative is I get x, right? And just to kind of see how this plays out, 0 to 1, x, and that's going to go from negative square root of 1 minus y squared to 1 minus y, and then dy. Okay, so then we put those limits in. So we have 0 to 1, 1 minus y minus negative square root of 1 minus y squared dy. If you guys can remember back to, some of you did it in Calc 1, some of you did it in Calc 2. This is just the area between two curves. Right minus left, or top minus bottom. So when that integrand is 1, you're actually really just doing a Calc 1 problem as a double integral problem. And the reason I want to make that comparison is because think of your region in that way. Think of back to how you did area between two curves. Remember, top minus bottom, right minus left. That's all we're doing for those, right here, for those inside limits, right minus left. Two last things I want to show you. One is, sometimes we want to switch the order of integration, okay? It'll make the integral easier to do. And so when this happens, we need to be able to come up with a rough idea of what our region looks like. And you can use graphing utilities to help you graph these. So our region is given by the limits. So our region is, y is in between 0 and 1, and x is in between e and e to the y. Is everybody seeing where I'm getting those? That's what makes up our region. So we need to be able to go back and forth. Okay, so now to plot this, we've got to be a little strategic because it's not super obvious if you haven't done it before what the curve x equals e to the y looks like. It looks like y equals e to the x turned on its side. What does that mean? Well, find its inverse. The inverse of this guy is y equals natural log of x. So that means that curve looks like this. So this is the curve x equals e to the y. So that's basically forming the left hand of our region. The right hand is a constant at x equals e. So that would be a vertical line there, x equals e. Y is going from 0 up to 1, which is where these intersect, because if this is the line x equals e, this is going to be the point e comma 1. Okay. There's our region. The problem is our integrand is not trivial if we have to do x first. So we might want to do y first. All right, so let's see what that's going to look like. So now instead of going left to right first, we're going to go bottom to top first. Meaning we're going to use the inverse, right? So the inverse of this, as we just said, is y equals ln of x. So now we're going to go from 0 up to the top. We can see it's the same top the whole time. So it's not going to make for an extra integral, 0 to ln of x. And now we'll go left to right. So we're going to need this point out to e. Well, this is where ln of x hits the x-axis. This is the point 1, 0. So x is going from 1 out to e. X over ln of x, but now we switch the order. Nothing we did messes with the integrand at all. Okay, all we did was switch the order of integration, switches our limits. So first thing now is we're going to integrate with respect to y. So we're going to add 1 to e, and this is going to be x over ln of x. This is all a constant with respect to y times y, and y is going to go from 0 to ln of x. Let's move that side over here. And then we'll do x in the next step. You can probably already start to see why this was so nice for us. Look what happens when I plug that ln of x in. I end up with x over ln of x times ln of x minus 0 dy. Those cancel, minus 0 is nothing. Oh, sorry, dx, excuse me. And all I have left now is 1 to e of x dx, which is x squared over 2 from 1 to e, or e squared over 2 minus 1/2. So this is a case where switching the order of integration makes it easier for us to calculate. Now, if that's what you're supposed to do in a problem, unless it's maybe a tougher problem in the homework, it'll tell you, like, switch the order of integration so you can solve this one. So don't worry about always having to figure out the order. But there are going to be some where you have to draw the region and decide which order you want to go in. Okay? Questions about this one? Okay, we're going to begin some practice here in a second. One last thing I do want to show you, and just to make sure that everybody's aware of it. So I know we've talked a little, you see me use Wolfram Alpha in here once in a while, and I use Symbolab as well. I want to show you just one thing. Symbolab is real nice for double integrals. Because what you can do is you can actually use the notation. So 0 up to 1. And then you can put in the inside one. 0 up to x, and maybe you have a function in here, x plus y, and then you tell it the order of integration. Now, because I have x on my inside limit, that tells me I have to do dx the second, okay? Now, I think you don't get the steps unless you have a membership, but again, that shows you some of the steps. But I want to make sure everybody, some of you folks I know already are aware of this, but I want to make sure everybody's aware of this. Like, this is a tool you guys can use. Obviously, you're going to have to be able to do some of them by hand for the proctored exam. But what about the take-home problems, right? Don't kill yourself doing double and triple integrals on the take-home problems, because honestly, the majority of the work is in setting them up. All right. Feel free to use Symbolab to check your answers, because here's the thing: double integrals aren't as bad. When we get into triple integrals, they can take a long time to calculate by hand. And think about a homework problem, right? You want to make sure it's set up right before you start to solve it by hand. Symbolab is a way of doing that. Okay. And the nice thing about Symbolab is the notation is the same that we're used to. You can do double integrals in Wolfram as well. Yeah. You absolutely can. You can use it knows if you use int, it knows what it means, or you can say integral. But Symbolab is a nice one to use as well. All right. So when you're working on homework and you're not getting, let's say you don't get the right answer on it, put what you originally had into Symbolab, check your answer and more, because that way you know, oh, it's set up wrong versus you made an error in the calculating steps. Yeah.